version of this presentation because it's normally a presentation I give to startups, actually here at Hacks, and other places about you have your idea, you've got your stuff together, and now how do you talk to the factory? Right? So we spent some time this week visiting a bunch of factories, seeing the processes on the inside. So now how do we actually engage them? So the overview we're going to talk about today is we're going to talk about documentation, which is everyone's favorite subject. I know all of you joined the PhD program because you went to do documentation. It's absolutely your top reason, which is what I'm going to talk about first. Design for manufacturing, I'll probably very quickly go over because it's not, you guys don't care about this at all, I don't think. You're not trying to make a profit, trying to just get a paper out. But this is part of a standard presentation I normally give to people who are going to do that. We're going to talk a little about testing the thing that you built. Maybe you want it to work, maybe you want the factory to know if it works, so we'll cover that shortly. And a bit about design process and picking a factory. So, that's not good. Let me readjust my screen resolution so I don't lose slides again. Alright, so any of you guys use Altium here? People, what do you use for your PCB design? Eagle? Anyone else do PCB design here? What else do you use?
Just Altium.
Altium. Okay. Really? No one else here does circuit board design? Only three?
They all use Eagle.
Oh, they use Eagle?
Yeah.
Okay.
まあ、キキャド
KiCad.
キキャド sometimes.
Fair enough. So, if you were to design, like I start with a simple example here. If you were to design a thing that flashes a light, right? Just want to turn on and off. I can probably actually just hand this bill of materials to anyone here in this room and say, build this circuit. I don't even have to give you the schematic. I don't even have to tell you what's going on here. You'll get it. 555 timer. You're going to put it in the astable mode. You're going to use the 10 microfarad capacitor as your timing capacitor, and the larger resistors you're going to use as your timing resistors, right? This is like just a stop circuit, right? And this is the bill of materials that typically will come out of an Altium tool for this. If you just use the stock library components, right? So it's a thing that that everyone here would know how to build the circuit correctly. But then if you handed this bill of materials to a factory here in China, you're not going to get a circuit that necessarily works out, right? There's a lot of things missing from this bill of materials. So yes, the key information is there, right? But things like, how big components are, what the tolerance is, like, a bunch of these things are missing by default, actually, from an Altium schematic, right? So some of the things missing are, let me get the next slide. Windows wants me to update my computer. Very aggressive, telling me that I need to update.
You're using a click?
So,
Clicker?
it's not a clicker issue. It's actually LibreOffice. It's not like doing well with high resolution monitors. So size is very important. when you say you want to have like a 10K resistor or something like this, they come in all shapes and sizes, right? From like through-hole components, surface mount components, these types of things. Capacitors come in many different sizes as well, right? So you could say you want a microfarad capacitor, but you know, you have everything from ceramics, tantalums, electrolytics, these types of things. Particularly when you specify ceramic capacitors, there's actually a 3-letter code, like X5R, Y5V, these types of things. Those are really important. They specify how the capacitor behaves over temperature and voltage. So the cheap ones actually have almost a 100% range in capacitance, right? So Y5V or something like this, they'll be up to plus 80%, minus 20%. So if you were to specify, if you didn't write down what you wanted in your bill of materials, your factory will probably give you a capacitor from this tolerance spec. It's the cheapest type of dielectric you can get. And so if you're using that for example, to adjust the timing rate of your flashing, you're going to have a huge variance across the production line in terms of the rate of flashing for these things. So if you just say, give me a 10 microfarad capacitor, you don't specify what dielectric, you can have a huge variability at the end of the day. I know that there's some Japanese companies actually that by as a matter of policy, they don't use tantalum capacitors anymore. So tantalum capacitors like that yellow one over there in the middle. And the problem with those is that they have a limitation where the inrush current, if too much current goes into it at one point in time, it'll actually catch fire, right? A little puff of smoke will come out. So the unfortunate part about tantalum, or the fortunate part, I guess, is that they have a very high value for the size. So if you want a 100 microfarad capacitor, tantalum will be smaller than a ceramic capacitor. So a place where a lot of them where we're getting used is in the input power to like your laptop or to your whatever your IoT device is, right? If you think about it, it's on the input power supply. You take your power supply that's already energized to 5 or 12 volts, and you plug it in. What happens, right? All of the power that's in this power supply instantaneously transfers into the capacitor that's sitting on the input there. So normally you wouldn't think about the inrush rating as a really important rating, right? But when you plug it in, you have this instantaneous, like several amperes if you don't limit it, current. So now you're on your workbench and you have this tantalum capacitor on your input filtering out all the noise. You can pass FCC, whatever it is. You plug it in, plug it out. Nothing's wrong. Maybe 100 times in your workbench. But they fail like 1 out of 10,000 times in this way, right? When you push it high. So then you go to production. The first 10,000 units ship, and someone posts on Instagram a picture of their unit, you know, with a scorched capacitor and smoke coming out of it, and now your reputation is ruined, right? So this is like one of those like tricky things about speccing out capacitors that a lot of people don't necessarily. They go, well, why do I care about what dielectric is 10 microfarad, 100 microfarad, use whatever I want, right? The dielectric actually has a huge impact on reliability, has a huge impact on the tolerance and the voltage levels, these types of things. When you specify a part number, so this here is a part number from what was National Semiconductor is now TI part, LM3670MF. Dash 3.3. So as engineers, we're just like, oh, okay, this is a switching regulator, right? 3.3 volts. We've specified everything. You put that down in your schematic tool, right? There's a couple of other characters here that don't seem to matter. There's like one with an X, one with a Y, and one without, right? Or something like this. And then this /no PB at the end. It turns out, for example, if you put it into your schematic tool, what you think is the interesting part of the part number, and you leave this off, just none of this here. It's a valid part number, actually. This missing is a valid part number. But what does the no PV mean? It means lead free, right? So you might put in your schematic without this piece here, hand it to the factory, and the factory actually give you a very good quote. No one wants leaded parts anymore today. They're like, oh, okay, this is great. Like, you know, we're getting a very good pricing on the parts. But then you try to import it into like Europe for Japan or something like this, where they have a lead-free requirement, and you can't get the certification for it anymore, right? It's because you left out this specifier, right? So basically, when you go and you try to enter in the part number from the bill of materials, you need to go to the ordering information, see all the options, and make sure you fully specify the part number. Another issue is a lot of times the part number, not only do they tell you what the voltage of a part is and what the part number is, they'll tell you how many come on the reel. TI in particular, they'll offer like 250 per reel or 3,000 per reel, right? And a lot of times, actually, if you go onto DigiKey, you'll be like, hey, they have cut tape, they're both the same part, and one's like 20 cents more than the other, right? And the one that's a little bit more is the one that comes on a slightly smaller reel, because you're paying for that reel and the handling costs of that reel. If you work with a Chinese factory and you don't specify this reel number or use a default, they will buy the amount that you specify, right? So if you wrote, because the part number for 3,000 on a reel had less characters, it seemed like whatever reason was the top on the list when you were entering in your Altium schematics, that factory will quote based on you wanting to buy 3,000 of these, right? And you want to build like 100, right? And so sometimes it seems to even work out okay. Like the factory will be like, oh, okay, like, buy the reel, we'll do the quotation, the pricing seems good. And then you say, okay, great, like we're finished doing our work, right? Then you get an invoice for 2,900 of these parts. And you're like, why is this factory billing me for like 2,900 of these parts? The factory will be like, well, you told us to order the reel of 3,000. We did the build of 100 of these thinking that you're going to do another several thousand of these units later on. And now that we're done doing business, you have to pay for these. And that's way outside your budget, right? Particularly if you're doing research, that you're gonna be really surprised if you have to pay for thousands of parts that you didn't want. So when you try to put your part numbers into your bill of materials, just pay attention to all those characters and make sure you're not accidentally ordering too many, accidentally ordering like a leaded part or a green part or whatever it is that you don't need at the end of the day. So if you were to throw LibreOffice out the window this morning, get there. If you were to actually take your bill of materials, that simple bill of materials I showed you before, and get it into a form that's ready for the factory quotation, it looks more like this, right? It's got a lot of information, so much it's actually hard to read. I understand. I'll talk you through it. So the quantity is here, the description is here, right? But now that 10 microfarad capacitor is now described as 10 microfarad ceramic, 16 volt, 10% X5R, right? So you've now covered all the bases. What's the voltage? What's the dielectric? What's the composition, right? You have the package, you have the designator, and then you have these things that are called AVLs, authorized vendor lists. So this is what you're telling the factory, for the 10 microfarad capacitor, I would like you to buy it from TDK, and here's the TDK part number, right? Not just a 10 microfarad capacitor, you're very specific. This is an important part, it's a timing capacitor, I want this specific part number, right? And then I also like to note in my personal bill of materials the minimum order quantity. So for example, some parts are 2,000 minimum, some are 10,000 minimum when you go into mass production, right? And the lead time as well. How long it takes, not from DigiKey or some distributor, but if you went to TDK directly and says, I need you to make these don't exist right now, how long does it take? It can be 12 weeks, it can be 8 weeks, something like this, right? And shoot.
Yeah, so if you've got a bunch of stuff left over because you're buying reels of 10,000, you need 3,000, whatever, does the factory just hold on to all the excess for you, or do they ship it back to you? Or both?
You can specify. So if you order, you can tell them, look, if I'm doing a small run, and it's a prototype run, right, and I want you to buy full reels. If your intention is you're going to build more of them, typically tell them to hold it, right? So we're going to go into mass production shortly. If you're just doing a prototype run, you say just give me all the wheels after it, send me an invoice, right? Because most of you are not planning to go to thousands of unit scale. I think you're probably just going to have to work with the factory, tell them what we're doing. New product introduction, MPI, a short run. If possible, get tape it like cut tape and then put it on the reel inside the factory or something. There's a bunch of things you can do to try to get around these MOQ limitations. But like the price of a capacitor just is like, or these small components just gets so high. Like here in Hachang, they can get like 10,000 of these resistors for about $4 or $5, right? And then on DigiKey, if you order like 200, it'll be $4 or $5, right? So sometimes, like particularly if I'm here in China, I will just go downstairs for resistors and capacitors, and literally buy the reel, even though I only need 100 of them. Because by the time I got it in through DigiKey, paid the import taxes, did the reeling fee, work with the factory, all this sort of stuff, it's a little bit more expensive for me to get that cut tape than it is to buy the parts in that format. But for ICs, of course, it doesn't make sense to spend thousands of dollars on a reel. So you get the cut tape in the factory, particularly if when you're quoting them, you're going to ask, hey, can you do low volume MPI? They'll have a procedure for dealing with smaller volumes. Yeah. So knowing the MOQ and the lead time will help if you do decide to scale up, right? So if someone says to you later on, hey, my research this is great, we want to go and productize this, and someone says, oh, how long is it going to take for me to build it? Now you have like the lead times for everything. Oh, 16 weeks is my longest one, so 4 months at least, right? If you're going to do a crowdfunding campaign or something like this, you don't say, oh no, tomorrow we can deliver. Not possible, right? You actually can look in your thing and know. The other thing about keeping track of the MOQ, particularly as you start to scale up, there's a thing that I call the hot dog and buns problem. Like when you have a party, hot dogs come in a bag of 8, buns come in a bag of 10, right? And so if you want to buy enough for your party, you're always going to have some left over. Either too many hot dogs or too many buns at the end of the day, right? So as you go to mass production, the minimum order quantities don't match up the quantities in the build. You're going to end up with some really expensive parts left over or some really cheap parts left over. Keeping track of that MOQ as you decide to scale up will help you make decisions as to like, what are the volume breaks. People say like, well, how does someone know that at 100 units it's cheaper, or 500 units, or 3,000 units? A lot of times the reason why it gets cheaper is because now someone can consume the whole reel on that build versus like trying to split a reel. Let me close these doors to reduce the noise here. So these first few lines up here are the electronics, the resistors, capacitors, and the IC. Down here is nothing electronic or directly electronic. It doesn't have any yet. But the first thing on this line is the PCB, right? So one of the weird things about these like Eagle or Altium is they don't put the PCB on the BOM, right? So you'll get the thing out and it'll be all the electronic parts that go on the PCB, but it's somehow implicit that this PCB is going to be built. If you actually send your bill of materials to the factory without the PCB as one of the things you want quoted, they will happily quote for you without the PCB. And the reason why is many people here will say, oh, I'm billing at King Credit, I will consign that PCB to you. Don't quote it with your vendor, right? That would be the indication when you leave that PCB off the bill of materials. So sometimes if you were to meet 4 or 5 factories, you quote them out, and you say, oh wow, like 2 of them have a really good price and 2 of them are much higher. I don't know the reason why. If you look carefully, sometimes it's like one of them included the PCB price, one of them didn't include the PCB price because you didn't leave that on your bill of materials. It's really easy to forget that one. The rest of the items here are all of the plastics and screws, packaging, whatever it is that, in addition to your product, if you care about that. So all you want is a PCB, blank PCB for your research, then okay, this is all you need. But if you want to ship a product to a customer, it needs to go into a case. It has 2 parts, it has screws on it, it has a plastic bag, it has a carton, it has a master carton, it has all this sort of everything. Every one of those pieces, and we did the tear down of those products the other day, every single one of those pieces you have to pay for. None of them come automatically, right? So, for example, I've had products where we're going to go ship them. They put them into my nice box, right? You know, ready for shipping, and they wrap them up in a pallet, and they say, "Okay, you're ready to go." And the problem is that that nice gift box, the outside of it, I think we have it over here. Yeah. Like these boxes here, these aren't. You can't just put this into FedEx and expect them to ship it and not have like stickers stuck all over it, right? It always comes in another outside box, right? It's called a master carton. And so what they do is they take these things and they pack them like, 20 or 30 into a carton about this big so that that you can handle it and it's about the right size. I had a product once where I didn't put the master carton on the bill of materials, and so they packed it into this form. And it was all like ready to go on a pallet. And then I said, okay, well, send it to the United States. Here's the address. They're like, really? You want to send like these boxes to the United States? I was like, well, I thought you put them in these brown boxes. They're like, you didn't ask for the brown box on your bill of materials. You didn't specify. So I had finished product, done on time. Then I had to wait 2 weeks for those master cartons to get built because I didn't tell them ahead of time I want this brown box to put these things in. And this was a startup, and we're like, need to monetize this inventory, and the invoice is moving, that sort of stuff. So it was like not a great outcome. So you need to think about like every single little bit and part if you're going to go into sort of production, what should go into the bill of materials. So there's a thing called the engineering change order. So when you have a bill of materials and you need to change it, it's good if you can document to the factory what the changes are, right? A lot of factories, some of them will just say, oh, Weixin, we can just like go back and forth and send things on WeChat. Particularly if you've got a binding purchase order for something, you don't want to just say, hey, substitute this part for this other one, because people don't know like who's going to pay for the old part, where does a new part come from, like can we confirm this in the bill, whatever it is. If they don't communicate it to their other people, it's not going to help you. So this is what my ECOs look like. You can use whatever format you want, but I will have the sort of the project that it relates to, the purchase order that I placed for the product. So there's actually a binding contract based on the purchase order. Like, hey, I want to 1,000 of these or 100 of these, whatever it is. I leave the background in for me to remember why I made the ECO. It's not really for the factory, but it's mostly for me, because the problem is as things get moving forward, it's easy for you to forget. Oh, I need to remove these 22 mega resistors. And here's why I did it, right? And later on, when the factory asks me, like, oh yeah, I did that, right? That wasn't you, that was me, right? Then it's a change detail. So here's what it was originally. At R2, we had a 22 mega resistor. The new one is don't put it in, right? And the result is a bill of material change only. Like just basically leave these parts out. And I'll say, for this parts, I know you already ordered them. I will pay for them, scrap them, or whatever it is, right? So this is material disposition. And then my version history. This actually particularly easy. The reason why I show it is if you look at the date of it, it was 27th of February 2014. Which is just before Chinese New Year. And so this ECO saved my butt, this written one, right? Because what happens during Chinese New Year, everyone goes home, they leave the factory, right? Everything gets lost. It's no one can remember anything when you come back. And so I came back and I emailed the project manager. It was in March, I said, hey, welcome back from Chinese New Year. Did you guys implement this ECO? She's like, yeah, we implemented the ECO. Okay, great. I slept on it. I just felt bad somehow. Something I had some intuition. I said, can you send me a picture of the circuit board in this area here to confirm to me that this ECO was executed? She's like, sure, no problem, right? It's done, but don't worry about it. She sends me a circuit board and the components are there. I specified them to be left out, right? So they still missed the ECO, even though I sent them in writing. And it turns out what happened is that they had this process in the factory to implement everything, and that the line workers were new. They came back from Chinese New Year, were just being trained and didn't know to look for the ECO at the time, and so they skipped it, used the old bill of materials, and put the parts on. But the good news is because I had this in writing and I had the date and all the email trail, the factory just covered all the costs of fixing all the parts, right? They didn't charge me for it, right? So when you get into working with the factory, particularly after you've like put a purchase order in, I think it's good to have like a documented way. It doesn't have to be this formal, particularly because a lot of you are in a much smaller prototype stage at this point in time. But if you ever do decide to scale up and you say, hey, okay, I put a purchase order down for this inventory. If you need to change something and ask them to scrap or buy new ones, the ECO is going to be very helpful for you to manage expectations with the factory. This section here in DFM is not as relevant because a lot of you are not worried about profit and loss, right? You're worried about getting your research paper at the end of the day. But if you are a startup, right, and you're building hardware, your profit margins are usually between 10 to 50%. If you're doing really good, it's 50%. If you're doing badly, it's negative, right? But almost zero at the end of the day. And so, your parts all have a statistical likelihood of being in a certain range of tolerance, right? A 10 ohm resistor, and you put it into the multimeter, it's not 10 ohms, right? It might be 9.8, might be 10.1, something like this, right? And then when you put all those things together, you're going to have some tolerance for those parts, right? If you're counting on your resistor being exactly 10 ohms for your circuit to work, then what may happen is you have a situation like this. Like 40% of the units fail, 60% pass. Okay? When you're prototyping on your desk in the university, okay, fine. 40, 60, I could show one to my professor, he's happy, the demo's done, we're off to the races, right? But then when you go to production and you have this situation, if your margin is only 20 or 30% and 40% aren't working, you're throwing them away, you're out of money, right? You're literally throwing away cash, right? So DFM is the idea of taking all those tolerances and pushing them over so that maybe only 1% is not passing, and 99% is passing at the end of the day. So component variations can be very subtle. For example, like if you want to control the brightness of an LED, right? Everyone here is probably familiar. LED plus resistor. This is a very, very familiar circuit to people, right? 3.3 volts consistent. If you want this brightness to be very consistent, one idea is, I'll use a 1% resistor, right? This 1% resistor is very precise, and I put the LED down. The problem is that what dictates the brightness of an LED is not the resistance below, not the voltage across it. It's the forward voltage, the VF across the diode, which turns into a current, right? It's the amount of electrons going through. It's that current number. And so when you work through all the math, you figure out how much current is going through the LED, which is proportional to brightness. You actually have about a 20% variation in lead forward voltage, and then because of the way this divider works, the impact it has on current is even larger, right? It can be up to a 40% variation in brightness from one LED to the other. So if you have a bunch of LEDs, 10 in a row, some of them are going to be brighter and some of them are going to be dimmer because of this particular issue. And so at the end of the day, if you wanted to ship a product that has that relies on the brightness of these LEDs being very uniform, you might end up with a fairly high failure rate, 20%, something like this, because you can't control that parameter. And so instead, a DFM exercise would go and say, actually, the parameter we care about is the brightness of the LED. And that is drawn from the physical principle of how much current goes through. So what we don't want is a voltage control. What we want is a current control. Right? A current controller is a much more complicated circuit. This is a current controlling circuit. This is a voltage controlling circuit, right? Normally, when you design, you wouldn't, if you're not thinking carefully about what is your real parameter, what your specification, you'll go with the easy circuit, right? This one costs about $1 in volume to build, like the current controlling circuit, but it will, even if your LED is completely, you can put just a completely different manufacturer, completely different thing in there, it will control the amount of current, which is related to the brightness of the LED. So if you put this circuit in, it will go ahead and reduce your failure rate. And even though you spent $1 for that circuit, if it improves your yield by like 19%, you end up actually saving money at the end of the day. So it's not an intuitive thing to think about, but as you particularly go through your designs, and you have any intention of making more than like one of them to get your research done, you might want to think a little bit about what are the things that are really going to impact the stability of the circuit, and try to make sure you're controlling those parameters before you go to manufacturing. So after you finally build your circuit and you send it to the SMT line to put the parts on, how do you know it works? Right? Like these people.
Yeah, it's jumping.
Yeah. There's like so for example, there's a couple of problems here that are from actual circuits running. There's too much solder on this side here, and there's a short circuit right here. Right? Very, very tiny. These are tiny parts. There's a pair of resistors here. There's a tiny whisker of solder in between these two resistors, right? Like these types of problems happen on the SMT line, and so then how the factory has no idea even how these are going to work. Another problem, for example, is this is a QFN, right? These, this is actually a really common issue where you have like a small short circuit like between two pins on the QFN. QFNs are actually, in my opinion, more difficult than VGA for yield, because the QFN, they have the metal pad on the bottom side with the solder. That when the solder gets up to temperature, the flux will volatilize and then gas will come out, right? And then actually what can happen is the gas will come out and make the chip jump off of its pad slightly during that time. And so you get QFNs that will have this like, they're mounted here, but then off by one pitch, right? Or you'll have the QFN that it kind of wiggled around and it'll pull solder across the two pins. This is like a really, unfortunately, common problem with the QFNs. With the BGAs, they tend to just sort of self-align. They're much easier to solder. Once you get the stencil right and you have the process right, they're more consistent in my experience. In the very extreme case, you have situations like this where I had a part. This is a FPGA part. It's actually quite expensive. It was on a circuit board that I was selling as a robot controller to a university, and I had like 3% of these boards failing in production, right? And I told the factory, just put them aside. Like, I'll look at them later. It's 3%. It's not a big deal, right? I'm pretty happy I was able to ship that many to start with. And later on, I got the boards back. And I'm like, what the heck is going on? I can't figure out what's going on. I hooked up the JTAG to the FPGA so you can read out all of the parameters, silicon ID code. It turns out the silicon ID of this chip didn't match the chip that I thought I was putting down. And then when I put it on a microscope, I noticed there's this like white rectangle right here on the chip, right? And it turns out that underneath that white rectangle used to be the letters ES for engineering sample. And what happened was someone in the distribution chain had gone and laser etched off the ES, the engineering sample marking. And so these were like pre-production silicon that Xilinx made, handed to partners to validate that the FPGA worked, and they were meant to be thrown away after that process. So in many applications that didn't care about the things that changed between pre-production and production, actually many users may not even notice like that change. And so the distributor was blending these sort of fakes in at about a rate of like 3% into the supply chain. But like my particular application cared about the silicon ID code and wouldn't boot unless the silicon ID code checked, right? And so I caught them at this particular game, and eventually we had big arguments, and that gave me new FPGAs, right? And we were able to replace them. But these types of problems, they do happen, right? It's a really subtle one. The reason why they were, my theory for why they were replacing these at like a few percent is that they probably only make a few percent margin, right, on the sale. And so if they can essentially get these chips that were scrapped, hide them inside the production line at a couple percent rate, they can greatly increase increase their margin. Right?
Mm.
It's a risky thing to do, but essentially they come back with double the money at the end of the day. And because in this particular case, the pre-production silicon and the production silicon is very, very similar.
Mm.
The same bit stream would work on it. It would seem to boot. It was like, it's only if you really tested for certain parameters you would even know this problem happened. Essentially, these guys are just getting free money for nothing, right? So this particular problem happens, and this is like not a terribly uncommon story out here in China. So I think you guys saw these sort of orange boxes or black boxes on the production lines when we walked around the factory. You know, you saw them all against the wall. This huge array of them. These are the test jigs. They're semi-automated test jigs, and I like to tell startups that go through hacks that this is the product behind your product. So you think that you're designing an IoT device, right? You know, and you're worried about the firmware on it and like the Wi-Fi and all that sort of stuff. How do you test that works, right? Think about everything that has to go into testing that, right? You have to be able to put the firmware on in the first place. So you need a JTAG interface. You have to test the Wi-Fi. So now you need a base station on it. You have to test the Wi-Fi performance. So now you're talking about RF measurement, right? You have to test that your sensors are working well. So if you have like a pulse oximeter or something like this, you have to have a human model of something in there to go ahead and confirm the pulse oximeter is working, right? This is actually a really complicated issue to try and work through. Oftentimes, in a research project, what you'll do is say, make 10 boards, give it to me in my lab, and I will by hand, one by one, confirm if I can use this for my research. That's the typical research situation. But if you say I need to build 100 of these for user testing, you don't want to be sitting, well, maybe you'd want to, but I wouldn't want to be sitting in a bench, one by one, testing 100 PCBs and then debugging the rest of them. So the factories need to have a test jig to know what's working, what's not working. Test jigs can get really complicated. So this was an example of a TV-tronics product that we had done back in the day. It was like this little sticker that had like an Tiny85 on it, right? Which is like this total low-end 8-bit microcontroller. And the point of this is that the test jig for it had a full Linux computer on the inside, had a full Linux SBC. So even though your product was this tiny little 8-bit controller, the test jig itself had by far more complexity. I finished the circuit board in like an afternoon essentially, but the test jig itself took about 2 or 3 months to complete to get this to production. I have a quick video actually of one of these test jigs. I'm gonna see if I can find it. I have a few. There it is. Where did it go?
Oh,
Why is it not moving?
with the upside?
Strange.
Mm.
Let me just reconfigure this resolution. Oh, there it is.
Mm.
So this is a tester for a motherboard, PC motherboard, right? And you can see actually the PC motherboard itself is sitting there, and it has like every slot, every feature has something plugged into it. It's not like they just like, oh yeah, these statistically work. We're not going to test the USB port. We're not going to test these ports. They actually plug everything in, and they boot Windows on it. They run like a test like on the audio to check that like there's no distortion, whatever it is. Like the whole thing gets tested, and so you can see here like every single part is put in on this board. Every single one of these boards, and they cost like $70 a piece or something like that. So there's a lot of effort that goes into testing every port, every piece gets something put into it to be able to run this test. The sort of the best tester I've ever seen. Many years ago, actually, we brought a group here to Shenzhen, and we went to the Huawei factory where they were building the Huawei mobile phones, and it was really interesting. We were in this room that's the size of a gymnasium, and there were like 200 testers in it, right? These little like testers, they're all empty, right? Just dark. And then there was in the corner. There's these two machines. They looked like something out of like Star Trek, right? Big metal boxes, machine, all sort of stuff. And a worker would just put the phone down into the machine, and then these little robotic arms would come up and like plug in all the ports, all the things. A little silicone finger would come down and hang out over the display, all this sort of stuff. It would go in and it would seal itself into this RF chamber. And in a course of about maybe like 30 seconds to a minute, it would test every feature of the phone, the camera, front, back, the LED. They had another camera that would check to see for bad pixels, RGB bad pixels, all sort of stuff. They would do that. That tester cost $1 million to develop. What they told me at the time, but it was worth it because it replaced that room before with the 200 test jigs that were dark. That was what it replaced. There's a lot of effort that went into that jig, but when you get into real high volume production, the testers are not an insignificant research investment. So, if you guys do ever end up, sorry, let me slide. If you guys ever do end up, if you guys ever do end up going towards volume production, and you want to design one of these things, here's a couple of tips. Right, try to cover 100% of your features because anything can fail. Power button can fail, a connector can fail, whatever it is. Like particularly connectors and buttons, they're electromechanical parts, so it's kind of subtle. But after you ship it to the user and the button's not working, it's a bad experience. You might want to think about how to internationalize your UI. So a lot of people think about, we're going to think about the wireframe experience for our product. I think about the wireframe experience for the tester. So the UIs themselves, the workers don't speak English, right? Or if you're going to produce in Mexico, right, they may not speak Chinese, right? So if you make the UI in Chinese, you have to produce in China. Maybe go to Korea, maybe go to Japan, maybe go to other places, right? So we try to, like all my test jig UIs, they tend to use icons or red, green light, these kinds of things to tell if something works or not. I tried to think about the person doing the test as well. So the guy doing the test is sitting there. You've seen the people in the factory now this week. They just stick the thing in, press a button, stick the thing like 1,000 times a day. It is a boring thing to do. It's very hard for them to maintain focus on that task. So I actually tried to design the test to get them more focused on it. So that on the product Chumby that I had made. There's a test where there's an accelerometer that you have to sort of make sure it works. It was a little like marble game that people could play, and then it would show you your score at the end of the day. And so the workers would compete to see who could like finish it the fastest, right? And so I got much more testing throughput because there's a little bit of a mini game that was built into every single test process. Another good story is that if your tester is finished or it fails, it's good to have maybe a beep or something like that so that the worker knows it's done. Particularly if your test, say, takes 5 minutes to run. The worker puts it in, he hits a button, and he walks away, right? In particular, they never know when to come back, right? Because they're not going to sit there and watch it for 5 minutes while it runs. So a small audible alarm or something like that, not too obnoxious because you've heard the factors how bad they can be. A little small audible alarm can help remind them to get the test, come back to the tester and reduce the cost for the testing. Ideally, you think about what happens when your tester needs to be updated. So a lot of times your firmware inside your device needs an update, but that means if you're running in production, you have to update the thing that puts the firmware in there. If your plan to update the firmware is I go to the tester and I log in and I update the stuff. Every time you push a new version of software, you're coming to China, going to your factory, and updating the firmware on the inside. So there's a bunch of different ways to do it, depending upon how good the internet connectivity is at your factory and whatnot. In China, because the internet connection is so bad, usually what I do is I put the test program on a USB stick, and I tell them I just mail them the USB stick. I say send me the old one, put the new one in, start the test, right? And then the firmware is updated on it. If you have a factory that has good Wi-Fi, you can set up a VPN tunnel to your tester. You can tell the factory plug the tester into the internet. It'll dial home. I can now SSH in. I can update things. If you have like a better internet connection. I worked with a factory in Korea once, and they have like gigabit internet at the factory. That was awesome. I just put a straight GitHub repo on it, and just a script they would double click on it would just do a git pull, and then it was like straight from what I was whenever I pushed my stuff, it would just update the factory infrastructure. So depending upon like how sophisticated the factory is, you have a range of options for updating your tester. Okay, so let's see what's the next section. Okay, so this section here is about the design process. Yeah.
So, like for most people that are actually going to manufacture a product, like if you're a small company or entrepreneur or something, you probably don't know how to make a test.
Yeah.
You haven't done it before.
Right.
Do people use services to design?
Oh yeah. That's a really good question. So for the test jig itself, if you don't know how to make a test jig and your product is very, very, very simple, like chibi drawings with LEDs, you can just tell the factory, I need you to test if the LEDs work or not, and they can hammer it out for you. It'll be like a couple $100 or something like this. But if you have anything where you have to load firmware on or wherever it is, pretty much you're going to have to do that firmware loading bit. There are people who specialize in building the orange boxes. These things you don't have to build, right? So don't waste your time 3D printing parts and CNC machining, putting pogo pins in. Basically, take your Gerber, say here's the test points, send it to the factory that says I would like a jig that I can put the PCB into and have the alignment pins and whatever it is, and the clamp and the pogo pins, and I'll put the rest in myself, right? And then usually I'll say specify have some stand-ups for a Raspberry Pi or something like that on the inside. And then for about $100, $200 in a week here in Shenzhen, they'll send you that thing, right? So if you're back in Tokyo or you're in Boston and you want to do this, you say tell the factory I'm going to need the jig itself. Please make that physical thing, mail it to me, and then back in your lab, you add the Raspberry Pi, you add whatever it is to the firmware updating, you put the firmware in there, and then when it's done, you can mail it back to them, and then they can run the production. That's typically how I would arrange this to be done. There are some open source testing frameworks. So Sean in particular, who's no longer here with us today, but he wrote one called Xclave. It's written in Rust. And it's the idea is that as you get your PCB back, you'll be like, oh, does the LED work? Okay, fine. I'm gonna write a little bash script that like lights up the LED, or like, does the accelerometer work? I'm gonna run like some I2C command that like checks the ID, whatever it is. These are a whole bunch of single point programs you wrote anyways, right? You had to do this to even know if your board worked. So the concept of Sean's infrastructure is take this collection of programs you wrote already, run them in a sequence in a scenario, and that becomes now your factory test. So you're not having to write things twice. And so Xclave is essentially a shell script sequencer. So if you do your bring up using like Windows or Bash or Linux or something like this, just keep a record of all the scripts that you ran. You can then install Xclave on a Raspberry Pi, load those scripts on it, and it'll do all those for you in sequence at the factory. Right? So there's some more automation that's happening in this area to help you with this. But that would be ideal, something like that. You guys all went to PCB factories earlier on this trip. When you get to to know your factory, you learn stuff about like the difference between solder mask and silk screen. I think I mentioned this on the tour. Arduino on the back side of the PCB here, they have like these really fine dots, and they also have a map of Italy in the back, right? And Massimo is very proud that like Sicily is separate from Italy. It doesn't merge into one blob because of the quality of the factory. It turns out the way they did this is they put it's not silk screen, they put 2 layers of solder mask down, first the blue one and then the white one. I didn't even know this was a thing. They even put multiple layers of solder mask on a PCB until I visited a PCB shop, and it's just a film they put down. It's actually pretty cheap and they put more and more layers on. So some people have gone nuts and put like 8 layers of solder mask on to build full like color graphics on the back of their PCB and then shipping it to people, right? So so when you go to the factory, and this is the reason why we go visit all of them, you can learn little tricks like this that can greatly improve your product quality without having to pay a lot of money. Because if you're trying to get that quality with a silk screen, you would hammer on the factory like, oh, we reject this. Like, you know, silk screen, the mesh isn't fine enough to do it anyways. You're at the limit of the process. You have like such a high scrap rate and such a dumb process step with silk screen, right? But then if you swap it in for two solder masks, then your yield goes up and your cost goes down. So you know, we go to factories to look at like molding processes. This one here is actually we talked about double shot molds. Putting 2 plastics together. This is what a double shot mold looks like. This one here is the hard half. This one here is the soft half. It's the same piece. And there's these 2 tools, and then every single time it shoots, they actually spin around, and then it comes and puts the other plastic on, and it spins back the other way, and then the worker can take the thing out. So it's actually it's a really bespoke machine to be able to do this double shot mold. Victor, he had some like non-waste product that he showed with the elastomer. That one is done manually. They put the hard piece in, they get the hard pieces out, and then in a separate step they put it in a tool with the soft pieces. They put the soft piece over. You can do that if the tolerance is pretty big on your elastomer step, but you're going to have a little more tolerance issue if you don't have the rotating tool. And so I didn't know about double shot tools when I came out here, and so we had this product where the industrial designer came up with this concept where he wanted the front bezel to have like this blue outline on the outside. A little bit, the idea was like a comic speech bubble. You know, when people in comics, they have a little speech bubble over their head. It was supposed to be like, oh, here's a screen, it's giving you a thought, right? That was the intention of the design. Turns out this thing is really hard to build, right? If you think about it, if you have a raised ridge and you want it to be a different color, if you're painting it, if the painting is not perfectly aligned, it's a little bit off on the side. When you look at it from the edge, you'll see even just a few microns of the blue coming off the edge. Your eye will see it immediately, right? It's total reject at that point in time. So we couldn't get the alignment there with pad printing. We couldn't get there with silk screening. We looked at all types of processes. What we ended up with is the same process they used to put the face on Barbie dolls. So Barbie dolls have like eyeballs and like eyelashes. There's a lot of fine structures put on her face, and it's all using this like sort of metal stencil they put on the face with the jig that aligns it. And they would use spray paint on top of it. So we used essentially the Barbie doll process to put this on. The yield of this process was 40%. 60% of the units were being thrown away. The cases themselves cost about $1 or something, and so we just ate it. We just had a huge pile of scrap. We would paint it and then throw away most of it, right? And then someone was like, why don't you use a double shot mold? So we first shoot white, and then we shoot blue in the mold, and it's gonna be injection mold. It's gonna be perfect every single time. I was like, that's the thing. And then they went ahead and we paid for the tooling to do that. It was expensive, but we're throwing away $1 a unit every single time, basically. The double shot tool got this perfect blue line every single time, just right, for a little bit of extra cost. So my suggestion for your design process is come up with your research idea and sketch it out, but don't fall in love with it, because your baby is going to be ugly, right? One of the dangers, particularly, you guys are PhD students, you're really smart, you think your stuff doesn't suck, right? The problem is that there's a lot you're going to learn along the way as you implement it, and you have to be willing to let go of some parts of it, right? after you sort of sketch your idea, break your design into material process categories. What I mean by that is like, so here's a remote control. There's a process category for injection molding. That's a process category. There's a silicone button. That's another process category. There's a PCB on the inside. Another process category. So this one has like 3 different processes. Each of them are going to be different factories. So what you're doing is you're breaking down by material type to the factory that you've defined. Then find the factories, visit them on each of those key processes that you need for your design. Look at the factory and see what they're running down. So for example, we visit the injection molding factory. They do zinc. I didn't know this, right? That's that if you had started your design originally with the concept that you want to build something that had plastic, but then you go to the factory and say, oh, they can do this zinc, metal and plastic combination, maybe that would inform how you would do that's another capability that's actually kind of for free in a facility that can do that thing for you. So it's good to sort of visit these factories and see what's running on the production line, get some ideas, maybe inspire you, or like when we went to King Credit, and we saw them there now doing all of these like really fine SMT with the stiffer on the backside. You get a better idea of how the flex PCB, what the limits of that process are, like how you have an intuition. You don't have to say go online and search for on Google like what are FPC design rules. It's all bullshit anyways on Google, right? So there's nothing better than going to the factory, visiting them, and finding out like what those rules are. After you've done the visit, reevaluate your design based upon what your factories can do. Right? Okay, this is easy, this is hard. Like maybe if I was just a little clever about the design or whatever it is, I can improve the capability. Right? This is the part where you have to throw away bits of your baby, bits of your idea to try and improve it for usability. And then only after you complete step 4, worry about things like parting lines and sliding surfaces and draft angles, right? Don't waste your time at the design phase putting in like all these things we talked about for injection molding. That's just a waste of your time. The draft angle, the parting lines, the ribbing, sink marks, that's all dependent upon the capability of your injection molding partner. Some people can do it, some people can't. It's all a matter of cost, it's a matter of what they can do, their time, process time, and this sort of thing. After that, then you can go ahead and ask the factory to help you finalize that, do your 3D prints, whatever it is. And then finally, consider if you're going to tooling for plastics, what are tool safe modifications? As I was saying, like it's easy to remove steel, add plastic. Very hard to go the other way around. And then, or like for example, if you're doing electronics and you're not sure, you have some analog filter, right? You're not sure what topology it's going to be. Guess what? 2 shunts and a through is either 2 components that aren't there and a 0 ohm resistor, right? So you just put that on your board. Later on, if you need that filter, you don't even know what the topology is. RC is RLC, whatever is it. Guess what? 2 0402 pads plus a shunt 0402 pad gives you all the topologies you can get. You never have to remanufacture that circuit board. It's just a bomb change later on down the line. So thinking through your design a little bit like that, and trying to give yourself all of the saving throws you can before you go to production will make your life a bit easier. Any questions on sort of the process? This is actually at least the process that I use. You guys will all invent your own. Okay. So, did you want to take a picture of that? Picking factories. How many people here have seen Harry Potter, right? This is not like a thing that I'm too old or something like this anymore. Sometimes I talk to like younger audiences, I have to remember people don't know what Back to the Future is, stuff from the 80s, but you guys are all old enough to know Harry Potter, right? So in Harry Potter, there's a scene where Harry Potter picks a wand, and he goes to this alley and he meets the wand maker, and the wand maker says that the wand chooses the wizard as much as the wizard chooses the wand, right? So here in China, the factory picks you as much as you pick the factory, right? walked into the factories this week and you saw they're really busy. They have a lot of utilization. Most of them have pretty high utilization, right? How is it they're like, you know, how is it that they're always doing something, right? It's because they're picking customers. They have more customers than they need, actually, most of them have. And so they have the ability to be like, I would prefer to do business with you than not you, for whatever reason. So one of the things that you're doing when you come out here to visit the factory is not just, like, you can go on AliExpress and source these guys all day long and try to do it on a internet handshake, right? But if they don't like your design or what they're trying to do, they'll just send you something half-assed. Just like, whatever, we'll fit them in the Go shift and send the stuff off. He sends you the money anyways. You can't, you know, whatever, right? But if you meet the factory and they like you and they want to put you on the production line, you can get a, you know, much better service. You get an idea of what the capability is. Like, you actually, like, one thing I like to know is, like, who are their engineers? Who is the tooling engineer? Who is, like, the DFM engineer? Who are these guys, right? And they'll have, if you go to a factory, sometimes they'll trot out, like, their best guy, whatever it is, but actually he's got, like, 3 interns. And when you put your product in, if you're being assigned one of the interns, look out, right? You're not actually going to get that good guy's attention. And it's okay to work with the interns. It's not like, realistically speaking, if you're doing a very small volume project, that's what you're going to get. However, knowing that guy's name and being able to escalate to that is very helpful. At some point in time, if you're not making progress on your tooling design or your DFM, you can say, can we get John back into the room and have him take a look at this? And then they, oh, okay, that's a good idea. Yeah, let me get the boss in and he can actually try to fix the issue, right? So that's the difference of actually meeting the people, knowing what's going on the inside. So I like to model the design process not like you versus the factory, but you are in the factory and the factories and you're working together and trying to build something. You're partners in this, not like master-slave relationship or client, sort of client-server relationship, right? And so when we visit the factories, you'll have noticed every single time when we went, I would bring the boss to lunch, right? We would eat dinner with them, and I would want them all to meet you. You know, have a glass of Baijiu with the boss or something like that. That's building that relationship, like the beginning of building that relationship that will allow you. So now, when you go ahead and send a message to King Creddy or to Red Lee or to one of these factories that we went, you have a little more context. You have something to start with as a relationship. You can cultivate that, right? And so a lot of the reason why you're out here in China is to try and build those relationships. That's what you're going to take home with you to Tokyo. That's what you're going to take home with you to Boston, right? It's not the bag full of circuit boards that you bring back. I mean, it's great if you come back with one of those, right? But the thing that's really going to get you going beyond your research and moving forward quickly is that relationship to be able to do the next set of circuit boards. This slide is more for the startups that I give this to, but it's probably a reasonable thing to bring up. If you're a startup or a research group, you have a limited amount of cash, and the factories know this. They're not idiots. They're not going to be like, hey, we're going to work with the research group because they're going to make us rich, or hey, we're going to work with a startup because you're going to like make it rain, right? This, like, even if you just closed Series A and you have $2 million in the bank, maybe 10 years ago, the factories here didn't understand what Series A meant, right? But now all the factories, if you say, hey, I'm a startup, I did like $2 million, they're like, that's gone in 6 months. Like, screw you. Like, what's your product, right? What are you really trying to do? Like, is there a real opportunity here? And so if you walk in and you say, hey, I'll pay for everything, just don't worry, again, money. Like, we have a research budget, we're from the Media Lab, we're super rich, we can just go ahead and just spend our way up. And the factory, like, okay, sucker, like, I don't really care, we'll take your money, you're not going to do a good job on it, right? Really what these factories are looking for is, particularly in the research, like, can you improve their process, right? So Wang Zhong, the guy who ran the printing factory, multiple times said, you look at the product sample room, right? All of them look pretty similar, like bags, boxes, shoe boxes, these type of things. But when people walk into the room and they see the Chibitronic stuff, that's different. business because he can put those things there and show customers this interesting product that few other printers can even do. And so that's been his calling card now to try and build business. And so, part of the reason he's willing to humor us, bringing a group of 18 people in the factory, wandering around the line, sticking your head inside the machines, whatever it is because, in the process of doing this research, we gave him a capability. And he values that, right? So if you're working with some of these factories and particularly that you want to build something that's a little bit difficult, but you're not wanting a lot of them, ideally you're leaving them something non-tangible. Like you're improving their design, you're improving the specification, you're giving them new capability, they're working with you in some other way. So it's not just about money, it's more about what value do you bring from like a technology capability or a human resource standpoint. It's easy to know the cost of your product. You can go to DigiKey and find the price of anything, right? But it's hard to know the price. So a lot of times when you finally get that quotation back and you say, oh, this factory is like so much cheaper than this particular factory, I'll just go to the cheap one, right? Like it's hard to know actually what's built into that final quotation. You need to look at things like, are they going to do DFM for free? Do you get tooling revisions for free? Is there a line fee that they're going to charge you to set it up? If you have your parts come in, you're scheduled to produce on July 15th, but then there's a customs issue and you have to do it on July 20th, they're going to charge you $200 for a line down fee, right? Because the problem is they scheduled you to run that day, that part's missing. I know it's not your fault, but the problem is that line isn't generating revenue that day, right? And so a lot of times there's these little details that are sort of implicit in different quotations. So one factor, we just charge you cost price, set up the SMT machine, run it. But then if anything goes wrong, you pay. Another factory will be like, you're like, wow, it's like setup fees like a couple $100 and you're charging a few dollars a board. It seems really pricey, but they're very flexible. Everything is, the answer is yes at that point in time because it's built into the cost, right? If you go to the factory and you don't visit, you don't see the CEO or the head of the factory, maybe they're a little too big for you at this stage, right? Because particularly you're looking to do something a little bit weird, right? Of course you can go to Foxconn and ask them to do your work for you. It's just money at that point in time. But then there's no advantage, I think, in this situation. This applies to factories back domestically in your home country as well as here. If you can visit the factory boss, I think that you can get a little more progress done quickly. And transparency is good. So when you get your bill of materials quotation, if they're willing to sort of line by line show how much something costs, what goes into the product, that's a good sign. If they just say, here's your cost price, no breakdown, then that's a bad sign because they can go ahead and just hide costs inside the product. They're just trying to make money that way. This is the last slide. We'll go through it just very quickly. Make sure that you understand how your excess is being handled. So if you order like a reel of 1,000 and you only want to build 100, when do you pay for that? How do they hold on to it? If you're going to scale up, having a plan for how to handle the worst case scenario, like hey, like all the units need rework because of some issue. How are we going to deal with this, right? Having to be able to have that conversation is a helpful thing to have with the boss. If you're planning to do like a user test study and you need like 100 units, consider building like 120 or 150 of them because some of them aren't going to work. Some are going to get broken. There's a whole bunch of things. So order a few extra units beyond what you absolutely strictly need. Because if you needed 100 units and one of them is broken and you have 99, you can't just go back to the factory and say, hey, can you fire up that whole line to build one? Right? They'll want you to build another 100 units for that one missing one. So it's much easier to sort of throw an extra one in at the beginning, build a few extra versus like asking the factory to go ahead and build a bunch later on. Shipping costs are a thing that really builds up quickly. I mean, I guess if you guys have a university budget, you'll never see it. But if you're a startup, start to get the FedEx bills and they're like a few $1,000s a month, they can really weigh down on your bottom line. And so you have to just like not just last minute everything and split everything into small shipments. Being a little strategic in how you do your shipping will help save you money. And the final item is particularly with the trade war going on, duties and tariffs are going to be an issue for the Americans. I think the Japanese still can pretty much do okay business with China, but on the America side, it's like some days you're paying 25% to get your prototypes in, some days it's duty free, right? And being being able to understand how that works and keeping a beat on that, making good HS code will save you a little bit of money, a little bit of headache. So that's the talk. Any questions?
May I ask about ECO? In prototyping phase, there no need of ECO to change the ECO, but after mass production needs a ECO. When start to the ECO, every change doing the still using same ECO.
Yeah. I think your question is when do you start doing the ECO in the process? My rule of thumb is after you place a purchase order. So if you're just in the quotation phase or prototyping and you haven't asked the factory to do anything, you don't. I mean, whatever it's in your head. Right?
Maybe the different contract and different paying after BCO or before PCO.
Yeah. The ECO will affect the price that you pay.
Okay.
Yeah, and so usually if you place a purchase order and you say, I want you to bring in 100 of these microprocessors, they're very expensive, and you want to change it to a new model number, you definitely want that in writing, right? Because you want to be clear with them, either you're canceling that order, or you're going to refund it, or you're going to sell it to someone else, whatever. So it helps to have that in writing formally, not just a WeChat. Hey, U1 needs to be a STM32F04C, not X, right? That's going to get lost. It's going to be a disaster if you don't get that in writing.
About the bomb, the one that had all the components on it, and you had also not only the electronic parts but also all the plastic parts.
Yeah.
So that list you sent was it for was that company to also build the PCBA and also the product itself?
Yeah. So this is like the full, if I were to ship something in a retail box.
So if you were to visit many vendors and for factory A to ask them to make a PCB and factory B to ask them to make PCBA and factory C to make an injection molding part, then we should ask and make a different bomb for each factory. Then also prepare a different one that for the assembly company that from this PCB and PCBA and this plastic parts come from each factories.
Yeah, if that's how you're going to do it, that's correct. So you would break this down. Say if you have one shop doing the PCB and another one doing the plastics, you wouldn't give them the whole bomb, right? This would go to the PCB shop, and this would go to the plastic shop, and then if you have a different one doing assembly, then you would have to pull in all those parts, right? Usually, what happens though is when we look at the SMT line, they don't just do SMT; they usually do the box build as well, right? They'll oftentimes want to deal with everything else. So typically, if you're looking to have a finished thing, you send them that bomb to the SMT shop, and then they'll help you work on sourcing other pieces. So there's another manufacturer that we're going up towards Dongguan. We're actually very close to the offices of a place called AQS, and they're like a full assembly shop. So if you need to have a large number, a few hundred pieces or something put together, they can help you coordinate, source, deal with the factories, so you don't have to deal with each individual one yourself. The downside of working with them is that they're going to work with their preferred vendors. So if you're like, hey, I want to work with this, I found this plastic shop or found this whatever PCB shop, they don't want to use those guys. They want to use their own preferred vendor. Right? So it's a trade-off between the questions?